You're sitting outside one day with your sister, laughing and smiling. Little do you know that this is the last conversation you'll have with her for a while. You see her get worse and worse over time until she can't distinguish between shapes or even speak a full sentence. The doctors confirm the worst when the MRIs come back. Your sister has a brain tumor. But she's not alone. In 2020, over 23,000 other people are predicted to have some sort of brain tumor. Magnetic resonance imaging, or MRI scans, provide detailed images of the brain and are currently the most common way to find and detect brain tumors like your sister's. The process of segmenting the image into different parts is known as brain tumor segmentation, and it often uses simple machine learning methods in order to do this. The goal of brain tumor segmentation is to detect the location and extension of a potential brain tumor. And this is done by finding abnormal areas and comparing them to normal areas of the brain. Brain tumors, specifically glioblastoma, are really sneaky, and their borders are really hard to detect from standard MRI brain scans. What this means for your sister is that if a surgeon goes out to remove the tumor, they could accidentally take out a little too much gray matter of the brain that surrounds the tumor, which could wreak havoc on your sister's cognitive functions. In order to help improve the accuracy of brain tumor segmentation methods, scientists at universities in Canada and France developed a convolutional neural network, or CNN model, that uses input cascade architecture as well as two-pathway architecture in order to help improve brain tumor segmentation. For academic purposes, I went through and replicated the code of this project to understand how it works. Now, before we jump into the actual model, let's take a quick look at what datasets were used. So the dataset for this particular model was the BRATS 2013 dataset, and it consisted of 4 different types of scans: T1, T1C, T2, and T2 flare. Each scan in the dataset was cut up into slices, as you can see with the ground truth label here. Now let's break down the model's architecture. The main aspect of a convolutional neural network, or CNN, is the convolutional layer. What's really neat about convolutional layers is that they can be stacked on top of each other to form a more convoluted network. A single convolutional layer takes a stack of input planes as its input, and then produces as output planes, or feature maps. If we have multiple convolutional layers in a neural network, what's really cool is that the convolutional layer's input is actually sometimes the output of the layer that comes before it. And this keeps happening as we have more convolutional layers, should they pass the activation function, of course. In order to create a feature map, 3 steps have to be taken. 1, we have to convert the input using filters or kernels. Then we have to apply the activation function, which in this case was the softmax function. And finally, we have to go through max pooling, which helps us identify the tumor more accurately. This particular model uses 2 types of convolutional architectures: the 2-pathway and the input cascade architecture. As its name suggests, the 2-pathway architecture consists of 2 paths: the 7x7 kernel, known as the local path, and the 13x13 kernel, known as the global path. This is done to ensure 2 things: that the visual details around the region of the tumor can be detected accurately, and to identify its context, its larger context, which is just basically the region around the tumor. You'll notice that the segmentation labels are predicted separately from the output. Cascaded architectures essentially connect the output of one node to transform it into the input of the next node, in a process known as input concatenation. The second type of cascaded architecture used in this particular model connected the first output to the second local path's first activation. The last type of cascaded architecture deployed connected the first output to the second output. In order to maximize the probabilities of all of the mini patches in the training set, gradient descent was used. Brain tumors make up a really small percentage of the overall brain. And even then, the proportions are such that these tumors make up an even smaller proportion of the unhealthy area. This is exactly why we use the two-pathway approach. The first training phase was conducted in such a way that all the labels in the dataset were equal probable of finding. In the second phase, all the outputs were passed through the kernels, this time with a more representative distribution of the labels. This was done to get the best of both worlds. Most of the capacity in the lower layers was balanced in such a way to account for the diversity in all of the classes. The output probabilities are then calculated correctly now that they have been adjusted for due to the output layer being trained on the correct set of data. Of course, dropout was utilized to ignore all of the irrelevant pieces of data. The results showed that this model was much more accurate than standard training models for brain tumor segmentation. This is really good news for your sister, because now she doesn't have to worry nearly as much as some surgeon just removing extra parts of gray matter from her brain. Maybe in a couple of months, you guys will be able to continue that wonderful conversation you had about the perfect weather. Hint, there's a right answer, and it's 75 degrees on a sunny day. Thank you so much for watching my review on brain tumor segmentation using convolutional neural networks. If you'd like to check out the code of this project, that will be linked down below, as well as the original paper and the article I wrote as a review of said paper. If you'd like to get in touch with me and learn more about the work I'm doing, my social media is also linked down below. Until next time.